Today we're talking optimization, which is a really fancy word of saying maximum and minimum, which we've been doing for a while, but these are different kinds of maximums and minimums. So first, I need to give you another theorem. It's a quick theorem. You're going to forget it because it doesn't have a fancy pants name. Well, I guess that's not true. It does, but you're going to forget this one. So your next theorem is called the endpoint Extrema theorem. And all it says is that if you are on a closed interval, so a function on a closed interval must have an absolute max and an absolute min. So more than just a relative max and min, an absolute max or min. And that should make some sense because if I close the interval under which you can graph and you have to end at dots, then you have to read an absolute high point and an absolute low point. The reason there has to be a closed interval is because those endpoints might be the absolute max and min. So you have to close your interval so that your endpoints are candidates. All right, that's it. So you should just be on the lookout for any time you have a closed interval and know that your endpoints could be potential maxes and mins now, absolute maxes and mins. So we're going to do 2 questions. Here's your first function. And let's go find, we're going to go find the abs max on the interval from 0 to 4. There are a couple different ways to go about this, and I'm going to show you all of them inside this one question. We're just going to talk about everything at once. So the first thing I need to find an absolute max is relative maxes. So we've been finding relative maxes when we were doing intervals of increasing and decreasing, and we're going to do it the same way. So we need a derivative to equal 0 to find critical points, which means I have to take a derivative. So f prime is 54 minus 6x squared. And when I set that equal to 0 to find these critical points, I get 2 values of x. So I'm going to add, divide, square root. I get x equals plus or minus 3. Sorry if that's fast algebra. You're welcome to pause. Remember that we are in the interval from 0 to 4, so we are only going to consider x equals positive 3. I don't need the negative 3 because it's outside my domain right now. Now we're going to do something called the second derivative test. Derivative test. So second derivative test is first going to require that we take a second derivative. So I have my first derivative over there next to me. My second derivative is negative 12x. And if you remember from last week, a second derivative tells you about concavity. So this value, x equals 3, I already know is a critical point, which makes it a potential max or min. Last week, we were doing those super fun number lines, and we could do that again, where we do f and f prime, and we could plug in to see if it changes from increase to decrease or decrease to increase. This is another option. If you're not liking the number line, or if you don't wanna, then you have this option now. So what we're going to do is we're going to take our critical point and put it into our second derivative. So our second derivative at 3, I don't even care what the value is. It's negative 36 because that's not bad. I care that it's negative. So here's what you got. You have a place where your derivative levels out. So your slope levels out. So this is a potential max or min. And you are concave down. So if you have a function that levels out and is concave down, what you've just discovered is that it is a relative maximum at that point. So now we know that x equals 3 gives a relative maximum. I don't know if it's the absolute. I know it's the relative. but that's step one. So a relative maximum could be the absolute maximum, or an endpoint could be the absolute maximum. So we go from our second derivative test to our candidates. So here are our candidates for the absolute max. It could be at 3, our relative min could be our absolute min. It could be at 0, or it could be at 4, because those are our endpoints. And this is so simple that it seems unnecessary. We're just going to plug in and find out. Let's go see what is f at 3, our original function, not our derivative, not our second derivative, because we're finding the absolute max of our original function. So it's all the way up there. I hope you have it written down. I hope you trust my arithmetic. Maybe you should, maybe you shouldn't. But these are the values I got. And just by testing those, I can see that, therefore, 113 is the absolute max. There you go. So there was a couple things in one. We took a derivative to find critical points to determine a relative max. You can still do a number line. You can still do a number line. A situation where you might not want to do a number line is like if you got 3 or 4 or 5 or 6 different critical points to test, and they could be ugly critical points where you don't want to put them on a number line. The second derivative test could be faster. Then we took those candidates and we just plugged them back in. So the question I always get, do I have to do a second derivative test to find an absolute max? Could I go straight from here, straight to candidates and plug in? Absolutely, yes. And maybe you should. Maybe it's faster. But maybe you had 3 or 4 or 5 different critical points to test, and you want to narrow those down before you go put them into your candidates, before you go put them into your original function. So these are all just options. There are quick ways to do it and not as quick ways to do it. It just depends on the question. And I cannot possibly give you every scenario. All right, here's your other one. Same thing. Here's x minus natural log of x. We're going to be on the interval from 1/2 to 2. And we are again going to find the absolute max. We're again going to find absolute max. So let's start by taking a derivative. 1 minus 1 over. We're going to take that derivative and we're going to set it equal to 0 to find our critical points. So if I add and multiply, I get x equals 1. Since that's just one value, if you want to, you can go straight to testing. So I can go find f of 1/2, f of 1, and f of 2 and see which one is biggest. And that's okay. That's fine to do. If you want to do your second derivative test, so our second derivative is going to be positive 1 over x squared if I pull a power subtract 1 again. And this is greater than 0 always. So what that means is this curve that we're dealing with in this interval from 1/2 to 2 is always concave up. Well, if it's always concave up, then this value I got over here as a critical point is a relative min. So I don't have to test it. And that takes away some of the work I need to do. So if f is always concave up, if f is always concave up, then x equals 1 is a relative minimum. And I don't need to test it if I'm trying to find a maximum. So this one, only the endpoints are possibilities. I used my calculator, and I got this, and I got this, and then you're just looking at values, and it looks to me like that's going to be our abs max. So was it faster not to test one? No, because that wasn't so bad. Again, there's options. All right, let me know if you need anything.